Hi guys, in Math 211 section 1 we see that a vector is an ordered list of numbers. This ordered list has surprisingly many applications to describe physical quantities such as force and displacement. The textbook has lots more examples. One that we'll play around with this semester is the application of vectors to the Pandora music service. Pandora thinks of a song as a vector, and we'll see that sometime later in the semester. One way to represent vectors is by the simple lettering U and V. Sometimes we put bars over the top, and oftentimes we don't when the meaning is clear. We also use arrows to represent vectors geometrically, as well as the list of numbers that I mentioned earlier. All three of these are different representations of vectors. Vectors can be added in the symbolic way by simply putting an addition sign between the two symbolic vectors. Geometrically, it works like this. For a white vector u, a purple vector v, we construct the vector u plus v. If we take the vector u and slide it along the vector v, the tip of the translated vector defines the endpoint of the new vector, and this new vector is called u plus v. Now, if u is given in terms of its components, and so is v, we can simply add the components to get the vector u plus v. 2 gets added to 5, giving me 7, 3, and 4. It also gives me 7, and 7 added to negative 1 gives me 6. So that's how we add vectors. We can also subtract vectors, and the way to think of that is simply to adding the negative. So if a vector u is given by the yellow, the negative u vector is simply the vector that has the same length as u and points in the opposite direction as u. So to subtract u minus v, first we find minus v, as shown, and then we add the two vectors. So we want to slide minus v all the way along u, and the new vector is the vector u minus v. Now if we have components, it's just what you think should happen. We're going to subtract components. So 2 minus a minus 2 gives us a 4, and 7 minus 5 is 2. Now, break. We can also do scalar multiplication of a vector. This is essentially scaling a vector by a single number, or scalar. So this number is called the scalar. And so in this case, 3 acts as the scalar, and we're multiplying 3 times v, getting a new vector. Geometrically, what's happening is we're taking the vector and we're scaling it in length by this factor. So in this case, a factor of 3. So this new vector is going to have length 3 times what it was initially. Component-wise, if we have a vector components, multiplying by 3 simply multiplies each component by 3. Likewise, if the scalar is negative, the negative gets distributed to each component of the vector. Notice that the multiplication by a scalar produces a vector that's parallel to what you began with. So in case, if you start with u, it's either going to be in the same direction or in the opposite direction, and those are all parallel vectors. Now, two vectors create endpoints. They create the tips of these vectors, and the distance, the difference to the endpoints of two vectors are points. And the difference between these 2 points is a vector, and it's labeled here as w. And so the difference between the vector v and u is a vector that connects the tip of u to the tip of v. So if I have components u1, u2 of a vector u, and components of a vector v, v1, v2, then if we take w, which is v1, the first component is v1 minus u1, and v2 minus u2, then this vector w will have its endpoint be at pointing toward v and its origin on the vector u. So this is the vector between 2 points. So for example, if we have the vector u, which is the vector given by the coordinates 0, 1, v, 1, 0, the vector between these 2 points is this yellow vector, and if we take u minus v, it will be pointing upward. To get the one pointing downward, we would simply have to take v minus u. Those would be equivalent vectors. All of these vectors live in a space we call Rn. We indicate a point in Rn as an n tuple, a simple ordered list of n numbers, and the set of all n tuples is what we call Rn. We live in R4, 3 dimensions for space, and 1 for time. Common notions of vectors. Now the 0 vector is the vector whose components are all 0. Adding the 0 vector to any vector does nothing. It returns the vector that you began with. Vector addition is commutative no matter what vectors you have. So u plus v is always equal to v plus u, and it's always associative. You can add 2 vectors and then add a third, or you can add the second and third and then add the first. Scalar multiplication works like so. If this is a scalar, a number, a real number, then if we multiply that scalar times the sum of 2 vectors, it's the same thing as multiplying the first vector by the scalar and then adding it to the scaled version of the second. 0, the number, is also a scalar, and if we scale of any vector by 0, we get the 0 vector back. So multiplying by 0 always gives us 0. That's comforting, right? Alright, there are many more, and I want to point you to page 9 to study some more properties of vectors in the algebra. So linear combinations turns out to be a very important idea in linear algebra. So suppose someone hands you 3 vectors, u, v, and w, all with the same number of components. We're going to form what's called a linear combination like this. We're going to take 3 times the first vector, add it to 5 times the second vector, and then subtract 7 times the vector w. What we're going to get is a new vector. This entire expression is actually a single vector, and it's called a linear combination of u, v, and w. It's got a little bit of u, a little more v, and then the opposite direction of w, all composing the vector. So for an example, if the vector 1, 2, 3 and the vector u, which is 6, 7, and 8, we can form a linear combination w as taking negative 3 times v plus 5 times u. So first we want to take negative 3v. So negative 3 multiplies by all 3 of these coordinates, giving us this guy. And then 5u is the vector here, which multiplying 5 by each of the coordinates here. Adding those two gives us a brand new vector, this guy, which we can think of as being a linear combination of v and w. So a linear combination is simply a weighted sum of vectors. You'll see in the textbook expressions like this, and these C1, C2, C3s simply represent numbers like 3, 5, and negative 7. So the CI's represent scalars, and this represents a general linear combination of u, v, and w. I also want to point out that any color can be thought of as a linear combination of 3 primary colors, red, green, and blue. So check the textbook for more. We'll stop here. Bye-bye.